Hey kids, welcome to section 4.4, graphing polynomial functions. Today we're going to learn how to evaluate polynomial functions and how to identify the general shapes of graphs of polynomial functions. So first we should probably know what a polynomial function is. A polynomial is written in standard form when the values of the exponents are in descending order. So all of the different expressions that are down here in this chart are all in descending order. X to the first, x to the 0, x to the second, x to the first, x to the 0, x to the third, x to the second, x to the first, x to the 0, and so on. The degree of the polynomial is the value of the greatest exponent. So for instance, the only exponent here is a 1, x to the first, therefore the degree is 1. Out of an exponent of 2, 1, or 0, 2 is the greatest, that's the degree. Notice also that a constant has an x to the 0 power, which is why it's always just a plain number. A linear function has an x to the first or a degree of 1. A quadratic has an x squared with a degree of 2. A cubic has a third power, which has a degree of 3. And in general, whatever the highest exponent is your n, which is your degree. And then we also have this other column called the leading coefficient. That's the number that's in front of the letter that has the highest exponent. So highest exponent is a 1, leading coefficient is 4. Highest exponent is 2, leading coefficient is 5, and so on. This is going to help us when we try to predict what the polynomial is going to look like when graphed. So state the degree and leading coefficient of each polynomial in one variable. If it is not a polynomial in one variable, explain why. Well, in letter A, make sure that you only have one letter going on. Make sure that it's also a polynomial. Problem is this is not a polynomial because you cannot have variables in the denominator. So this is not a polynomial. No variables in denominator. Remember, I can always bring that value back up to the numerator, but when I do that, it becomes a negative exponent, which again, you can't have any negative exponents either. All right, in letter B, make sure you only have one letter. Make sure there's nothing that's not allowed. I don't see anything. Degree here is 6, degree here is 4, degree here is 3, degree here is 0. Highest number is a 6, so the degree is 6. Your leading coefficient is the number that is in front of the letter with the highest exponent. Spelled that wrong. Fi coefficient. Yep. Okay, so if 6 is the highest exponent, then the leading coefficient is the 5, which is in front of it. All right, in letter C, we have a degree of 4, a degree of 3, a degree of 6, a degree of 0. No negative exponents, no variables in the denominator. We're good to go. It looks like the degree is 6. Don't think it's 4 because that's in the first spot. Make sure you look for the biggest one. And now that I know the degree is 6, I can find the leading coefficient. That's the number in front of the letter that has the highest exponent. That would be -1. Okay, in letter D, oh no, I have 2 letters in the equation. So this is not a polynomial in one variable. I have more than one variable in the problem. Okay, now we can do a lot with these polynomial functions. A polynomial function is a continuous function. That means there's no gaps. That can be described by a polynomial equation in one variable. The simplest polynomial functions of the form f of x equals ax to the b, where a and b are non-zero real numbers, are called power functions. Now, if you know an element in the domain of any polynomial function, you can find the corresponding value in the range by inserting the known value and calculating the function. Basically, you can use the substitution method. So here's a word problem. The volume of air in the lungs during a 5-second respiratory cycle can be modeled by V of t equals negative 0.037 t cubed plus 0.152 t squared plus 0.173 t, where V is the volume in liters and t is the time in seconds. Find the volume of air in the lungs 4 seconds into the respiratory cycle. Well, 4 seconds is time. Time is t. So I'm going to put 4 in for t. So I'm going to find V of 4 as negative 0.037 times 4 cubed plus 0.152 times 4 squared plus 0.173 times 4. When I do this, I get 0.756 liters. So I can find how much air is in our lungs by knowing how many seconds the air has been held. Now you can also calculate function values for variables and expressions. So I want to find g of 5a minus 2 plus 3g of 2a if my g of x equals x squared minus 5x plus 8. Well, I kind of have two parts here. I have g of 5a minus 2, and I have 3 times g of 2a. I'm going to find those separately and then add them together. So g of 5a minus 2 means to go to the g of x function and substitute 5a minus 2 in for each of the x's. So 5a minus 2 quantity squared minus 5 times 5a minus 2 plus 8. Well, 5a minus 2 quantity squared, remember, is 5a minus 2 times 5a minus 2. Yeah? So I double distribute. 5a times 5a is 25a squared. Then I do 5a times negative 2 is negative 10a. Negative 2 times 5a is negative 10a. Negative 2 times negative 2 is 4. Then I distribute. Negative 5 times 5a is negative 25a. Negative 5 times negative 2 is 10 plus 8. Clean it up, we get 25a squared. Negative 10a minus 10a is negative 20a. Minus 25 more is minus 45a. And then I have 4 plus 10 plus 8 is 22. That's my first answer. Now I got to find 3 times g of 2a. So I need to take 3 and multiply by whatever I get when I plug 2a in. So that's 2a quantity squared minus 5 times 2a plus 8. And so I'm going to have 3 times, well, 2a quantity squared is 4a squared. Then I have that minus 10a plus 8. Well, that's 12a squared minus 30a plus 8. There's my second one. So now I need to put them together. So I'm going to do my star plus my star. And I'm going to get 25a squared minus 45a plus 22 plus 12a squared minus 30a plus 8. So I just went and found my two expressions, and now I collect like terms. 25a squared plus 12a squared is 37a squared. Negative 45a plus a negative 30a is a negative 75a. And 22 plus 8 is 30. So 37a squared minus 75a plus 30. All right, letter B, we're going to find h of negative 4d plus 3 minus 0.5 h of d. if h of x equals 2x squared plus 5x plus 3. All right, so we want to first find h of negative 4d plus 3. So we're going to do 2 times a negative 4d plus 3 squared plus 5 times a negative 4d plus 3 plus 3. So this is going to be 2 times, and now I need to remember that this is negative 4d plus 3 times a negative 4d plus 3. So I double distribute, I get 16d squared. Negative 4d times 3 is negative 12d. 3 times negative 4d is negative 12d. 3 times 3 is 9. And then I do 5 times negative 4d is negative 20d. 5 times 3 is 15 plus 3. And then collect like terms. Let's see. I got 2 times 16d squared is 32d squared. 2 times negative 12d is negative 24d. 2 times negative 12d is negative 24d. 2 times 9 is 18 minus 20d plus 15 plus 3. And then finally 32d squared. I got minus 24d, that's minus 48d, minus 20 more d is minus 68d. And then I got 18 plus 15 is 33, and 3 more makes 36. So there's my first half. Then I need to do 0.5 times h of d. So I'm going to do 0.5 times, take the d and replace it. 2d squared plus 5d plus 3. Oh, that's nice. Distribute the 0.5, d squared plus 2.5d plus 1.5. Okay, there's my other half. Now I'm going to take my 2 stars and add them. Well, in this case, we're actually going to subtract them because the sign in between is a minus. So my first thing is 32d squared minus 68d plus 36, and I'm subtracting d squared plus 2.5d plus 1.5. Okay, big reveal. 32d squared minus d squared is 31d squared. Negative 68d minus 2.5d is minus 70.5d. And then 36 minus 1.5 is 34.5. Whew, those are long. All right, so now that we know how to work with polynomials, let's talk about how we graph them. So remember that real zeros occur at x-intercepts. Super important. So the number of times a graph intersects the x-axis equals the real number of zeros. So for instance, if my degree is 0, it doesn't cross the x-axis at all. If my degree is 1, it crosses the x-axis 1 time. It's a linear function. If my degree is 2, it can cross at most 2 times. That's a quadratic. 3 times means it crosses the x-axis 3 times. That's cubic. A degree of 4 means it crosses 4 times. That's a quartic. And a degree of 5 means it crosses 5 times. That's a quintic function. Now, there's also such thing as odd degree polynomials and even degree polynomials. Odd degree polynomials are going to have end behavior that are opposite. So one end behavior goes to positive infinity, one end behavior goes to negative infinity. But even degree polynomials have end behavior that are the same. Either they're both going to go to negative infinity, or they could both go to positive infinity. Now I can throw even more at you because here's a graph that kind of pulls together everything that I just kind of have been talking about. The degree is even if the end behaviors are the same. So this top left picture and the bottom left picture. The degree is odd when the end behaviors are different. One is positive infinity, one is negative infinity. So we're going to practice writing end behavior again. We're going to practice identifying odd and even. and we're going to practice identifying how many zeros the function could possibly have. So let's see how this works. Find the following for each. First, describe the end behavior. Okay, so as x approaches positive infinity, f of x approaches, well, as my x's get bigger, my y's get smaller, so negative infinity. As x approaches negative infinity, f of x approaches, well, as my x's get smaller, my y's get bigger, so I'm going to put positive infinity. Part 2, determine whether it represents an odd degree or an even degree polynomial function. Well, since my end behaviors are opposite, it's an odd degree polynomial. And part 3, state the number of real zeros. Since it crosses once, twice, 3 times, there are 3 real zeros. Remember, there could be some imaginary ones, but there are at least 3 real zeros. All right, letter B for this picture, our end behavior as x approaches positive infinity. F of x is approaching, well, as my x's get bigger, my y's go down, so that's negative infinity. If I look at the other side, as x approaches negative infinity, f of x is approaching, well, as my x gets smaller, my y's get smaller, so it also approaches negative infinity. Since my end behaviors are exactly the same, this is an even function, even degree. And since my quadratic crosses twice, there are 2 real zeros. All right, kids, that's the end of section 4.4. If you have any questions, please let me know. And as always, keep calm and keep trucking.